Let's do a couple of two-dimensional momentum problems. We have an incoming hockey puck, essentially, hitting another hockey puck, but not dead center. It's off-centered so that they're going to spread apart. So the incoming object hits this one and bounces up like this. Where do you think that one's got to go? Yeah, it's got to shoot down here somewhere, but we don't know the velocity. We don't know the angle. But if there's no outside forces on this system, we know the momentum before equals momentum after. Now, you can't just do it as if it was one-dimensional. The momentum is a vector, and it's in 2 dimensions. So this is going to be the momentum before, 20 kilograms meter per second from this. Now the object comes in, bounces up here, so that momentum is going to go right here. Well, this must be the missing momentum that I need, because the momentum after has to add up to the momentum before, and that's what this diagram shows us. We'll break this up into components. There's the y component. Here's the x component. And that vector is going to have an x and a y component. This one has to be 9.2 kilogram meters per second because this plus this has to add up to the 20. The y component must be equal to the y component going up over here. Pythagorean theorem, and the momentum is 11.12 kilogram meters per second, but that's not the velocity, that's the momentum. The momentum is mass times velocity, so I have to divide by that mass, and I get 1.39 meters per second. On the momentum diagram, I can do opposite over adjacent and get this angle. I get 34 degrees. Now keep in mind that the center of mass is just going to keep on moving at the same velocity throughout the whole problem. Checking out the energy, we have 40 joules initially. I use 1/2 mv squared for each one of these, and I get 23.4 joules. And that gives me about 58% efficiency. If you look at the computer simulation, those problems in the beginning were 100% efficient. Now I have these two objects sliding along, and they're going to hit and stick because it's an inelastic collision. Even though it's an inelastic collision, the forces will be internal, and we'll be able to use conservation of momentum to find that final velocity and that angle. You should have 18 kilogram meters per second for the first object, 20 kilogram meters per second for the second, and I get 26.91 kilogram meters per second for this hypotenuse. Well, that's the momentum of the final object. Divide by the mass of 8 kilograms, and I get 3.36 meters per second. Inverse tangent, I get 48 degrees, and that's where the rect is heading. Do 1/2 mv squared for each object, and you get 94 joules of initial kinetic energy. 1/2 mv squared for the final rect, and we have 45 joules, so we lost a lot of energy because it's an inelastic collision. Now let's do an explosion. We have a 6 kilogram object. I put a little stick of dynamite in there and blow it up. When it explodes, we detect 3 kilograms moving this way, 20 meters per second, 25 degrees. 1.5 kilograms moving this way at 40 meters per second at a 35-degree angle. Where's the missing piece going? Again, the explosion is an internal force. However hard it pushes this way, it pushes this way, or this way, and this way. So it's all isolated. Well, let's take a look at the momentum of this object. It's 60 kilogram meters per second going this way, which gives us 54.4 kilograms meters per second in the x direction and 25.4 kilogram meters per second in the y direction. The momentum for this piece is going to be 60 kilograms meters per second. We have a 35-degree angle, and that's going to give me an x and a y component of 49.15 and 34.4 kilogram meters per second. This one has to cancel these vectors because they all have to add up to 0. The momentum before this explosion was 0, and the momentum after has to be 0. So look at this y component, that y component. This one needs a y component that'll stop those. That'll be 59.8 kilograms meters per second. Well, if this is 54.4 to the left and that's 49.15 kilogram meters per second to the right. Well, that means there's a net momentum to the left. We have to stop that by going to the right. It's 5.25 kilograms meters per second. And the Pythagorean theorem gives us 60 kilograms meters per second. But remember, that's a momentum. Divide by 1.5 kilograms, and you get a velocity of 40 meters per second at an angle of about 5 degrees. So what would these vectors look like if we place them all tip to tail? Here's the first one. Here's the second. And there's the third. They add up to 0. Now, if you watch the computer simulation, you won't see something that works out so neatly. You can see 3 problems just like these, different numbers, on the worksheet for momentum in 2 dimensions. A few more good ones in the chapter notes.